So we will evaluate two parts. We will evaluate these two parts. You can see we will evaluate these two parts, the first one and the second one, and then we will substitute the value inside this equation. Okay? Then we will substitute the value inside this equation. We will finalize this equation. So let us evaluate the part number 1. Let us evaluate part number 1. That is number 1, polarization conjugate n cross n is equals to, that is going to be remain as it is. This is A, B, C. A, B, C, the cross product of three vectors or three terms. We will have n dot n of epsilon 0 minus n dot epsilon 0 dot n. Okay, but you know that this is nothing but equals to 1. This is equals to 1, and what is going to happen is equals to 0 minus dot n, I star dot n, and this is also going to equals to 0. This is going to equals to 1. This is going to be 0 due to the orthogonal to each other. This both are over here. N is nothing but the unit vector. This psi or epsilon is nothing but the polarization vector. They both are orthogonal to each other. Okay, both are orthogonal to each other, so they are going to 0. Now, number 2 is this epsilon star n cross n0 cross epsilon 0 is equals to, this is nothing but ABC, remember, okay, into n dot n0 cross epsilon 0. So this is just the final term. Okay, this is just the final term. Now we will try to substitute all these values inside that the scattering amplitude equation, the final equation. Then we are going to get is A star ASC divided by D0. Okay, epsilon star is equals to k square by 4 pi integration of dq x dot e raised to I k n 0 of n x star dot 0 conjugate dot 0 x by epsilon 0 minus del mu of x by mu 0 into polarization vector cross unit vector cross the conjugate of polarization cross unit vector into the original polarization vector cross original unit vector. Okay, so this is nothing but the final equation after substituting all those values. Now over here, remember, this is been replaced by this term, this small term is replaced by q. Okay, where q is the difference of the incident and scatter wave vector. Here k of n of 0 minus n is equals to q is the difference of the incident and scattered wave vectors. It's nothing but the incident and scattered wave vectors. Okay, that is nothing but the difference. Now we have just obtained the equation. Okay, we have just obtained the equation, but now what we are going to do is we will take an example as what we have taken inside the scattering theory of dielectric sphere, then a completely conducting sphere. We have taken two type of examples. Okay, that is, one it was of a dielectric sphere and another was it was of a conducting sphere. Now the similar thing, we will be taking an example as a dielectric sphere over here inside the Born approximation, and we will try to find out the variation inside that equation which we have obtained in the scattering theory, and the equation which we are going to obtain inside this Born approximation. So the equation of the differential scattering cross section, the equation of the differential scattering cross section in that scattering theory in the previous lectures, that is maybe in the lecture number 3 or 4, and we will derive over here with Born approximation for dielectric sphere the equation for scattering differential scattering cross section. Okay, now so let us have a few words again for that. That is, now to establish the contact or the relation, or try to compare with the results already obtained, what we will do is we will suppose that scattering region is a completely uniform dielectric sphere. We will suppose that the scattering region is a uniform dielectric sphere of radius A in vacuum. Okay, of radius A in vacuum. So the sphere will be something like this. Okay, and it will have a radius A. It will have delta epsilon is equals to epsilon minus epsilon 0. Delta is nothing but the chain. Now remember, over here it is a dielectric sphere, so outside the sphere, remember, delta mu will be 0 and delta epsilon will not be 0. Okay, that is, delta mu will be 0 because it's a dielectric sphere, so it will only have electric properties. It will not have it will not induce magnetic dipole moment, so it will not have permeability. It will not going to change the permeability. Okay, now we will again write the scattering amplitude equation with respect to this sphere with the spherical coordinates. Okay, with spherical coordinate system. So polarization conjugate scattering amplitude divided by V0 is equals to k square by 4 pi. This we have taken out with respect to x by epsilon 0 dot star by, this is mu, that is phi by 2 pi integration of 0 to a and integration of theta is equals to 0 to n, 0 to n, where we have r square sin theta d phi dot e raised to I cube r cos theta dot d of r divided by x of this. These are some of the things which we have taken from the spherical coordinates. We are taking with respect to spherical coordinates. Don't get confused because some of the steps we may not have considered over here, because sin theta d theta and phi, those are with respect to spherical coordinates, and r square sin theta is derived from spherical coordinate. Let me explain over here, because this is the z axis. This is the z axis. Let me take another color. This is the z axis. Okay, and this may be the theta. This may be the theta. So you can have r. You can have r, or you can write down another thing. You can imagine in such a way. This is r. This is r. This is a. And this is epsilon 0, this is epsilon. Okay, so r sin theta. Okay, now over here this term will integrating, we will directly take the equation, we will directly take the solution of integration. We are not going to integrate all these equations, and we will get q square by 4 pi a cube multiplying and divided by a cube. We are just multiplying and dividing by a cube, so don't get confused. 1 0. Over here it will have 4 pi. This is of sine qa minus qa cos qa divided by a cube. Okay, all this value, whole this value is going to 1 by 3. Whole value is going to be 1 by 3. We are not going in detail. We are not going in detail of the individual derivations. Please note that, and this 4 pi and 4 pi is going to be cancelled, and within, for the long limit, for the long wavelength, for the long wavelength, the limit q of a will tends to 0, and we will get, this is nothing but the scattering cross section. This is nothing but the differential scattering cross section. Okay, the square of it. Differential scattering cross section is given by the square of it. Okay, differential scattering cross section is nothing, is given by the square of it. Let me write that formula again. Okay, this we have studied in the last, that we may just recall that the differential scattering cross section is given by ohms is equals to star ASC whole square divided by V0 whole square. Okay, so this term we have to just make it square. So this term we have to just make it square with respect to it, and it's going to be, and differential scattering cross section. So the final term, which is been given by Born approximation is equals to just making a square of it, that is ASC by D0 whole square. This is the whole square, okay, is equals to k raised to 4 a raised to 6 epsilon by 3 epsilon 0 whole square. Okay, so this is the final equation. This is the final equation of the differential scattering cross section. And now we want to compare this differential scattering cross section which we have derived from the Born approximation. We will try to compare with respect to the original one which is we have been obtained in the third or fourth lecture with respect to dielectric sphere. Okay, and that was if we compare the above equation with the equation of dielectric sphere, which is d rho by d rho is equals to k raised to 4 k raised to 6 epsilon minus epsilon 0 minus 1 by epsilon 0 plus 2 epsilon star dot epsilon 0 whole square. So that is near about same. You can see the order is same. The order is same. You can see the order is same. Don't get confused about this delta epsilon and 3 epsilon. This can be converted to delta epsilon. Okay, this can be converted to this is nothing but this will be nothing but epsilon minus epsilon 0 divided by epsilon plus 2 epsilon 0. Okay, taking an LCM, okay, plus epsilon 0 minus epsilon 0. So this will be 3 epsilon 0. This both term, this two term will make 3 epsilon 0. Epsilon plus 3 epsilon minus epsilon 0. This can be neglected. This can be neglected due to the small variation. And this can be neglected. We will have 3 epsilon 0. So delta epsilon by 3 epsilon 0. So this will be near about delta epsilon by 3 epsilon 0. Okay, it will be just near about it. Don't get confused. So this is near about the same equation. You can find out the order is same. The order is same. Okay, the small variation is with respect to the Born approximation which we have did. Okay, so this is the end of the theory for Born approximation. Okay, thank you.